Now, at this point, the question is, how do people get the knowledge about the crystal structure, right? This is what we will talk about today. Okay, and so let's just jump right into the lecture. Um, Information about the crystal structure is obtained using X-rays. Um, Now, just so we understand what kind of X-rays we're using, right? The X-rays have about the same wavelength as the distance, between the crystal lattice planes, right? So now that you're familiar what the planes are, and if you have to, so basically that interplanar distance that we just looked at before, and you guys now already know that the numbers are extremely small. Usually it's in the range of zero point 0.5 angstrom to 2.5 angstrom, right? Or you can keep the nanometers as they are on the slide right now, 0.05 to 0.25 nanometers. Uh, so we're using the wavelength that is very, very similar to the distance between the adjacent crystal lattice planes, right? Now let's look at the concept because it is relatively simple. Like, how do we generate those X-rays that allow us to gain the information about the crystal structure? All right, so uh, to begin with, we need to have a target, okay? And we're gonna load that target, everything is in vacuum, okay? Now, we're gonna also use a tungsten filament, right? And you guys remember that tungsten has an extremely high melting point, and this is why we're gonna use it. Now, tungsten is connected to the transformer, and the voltages that we're using is something like 35 kilowatt, right? Very, very large voltage. And the idea is that once the voltage is applied, and then the tungsten filament also plays at the role of a cathode. The tungsten is our cathode, and the target itself is our anode. Once the voltage is applied and tungsten is heated up, it's gonna release a bunch of electrons. Okay, perhaps let me do this. It's gonna release a bunch of these electrons, and we call it a thermionic emission. Okay. So when the electrons, when the material, when metal is heated and the electrons are emitted, now because there's a voltage difference between our cathode and anode, these electrons are now um, accelerated toward the target. Okay. And once these electrons hit our target, and the target is what we were trying to study, we want to know the crystal structure. We want to identify, well, first, not just the crystal structure, we want to identify what kind of element it is. What happens is that this produces the X-rays. Okay. And I'm about to explain you what happens in the material itself so that the X-rays are produced. So once again, the electrons are accelerated toward the target, and then that produces the X-rays, right? We collect these X-rays, and we usually have these beryllium windows that allow us to collect these X-rays. Keep in mind is that we are talking about a very, very significant amount of energy, and this is why the target is usually it is heated as well, and this is why we usually run some cooling water, right? We need to run the cooling water through the target so we can cool it down, right? Now, you at this point, you're probably wondering, okay, but why does the target emit the X-rays, right? Well, usually, first I'm going to show you what you usually see on the software, right? You will see a spectrum that would look something like this, and you will see these characteristic peaks, okay? And these peaks are unique for every single element that exists in the world. And this is how we can identify. And when I mean the unique, I'm talking about this position, right? This position is going to be very unique. For example, for molybdenum, this K alpha, and I'll explain you what the K alpha is in a little bit, is located at about 0.07 nanometers. right? And then K beta has another value, which is again very, very unique and it is very, very specific for the element. Now, but what happens in the material so that we see, well, obviously we see radiation, but we also see these characteristic peaks? Well, this is what happens in the material. The electrons that are accelerated toward the target, they knock out the inner electrons from the metal. So if you guys remember at some point, and I'm going to keep a very simple structure, you guys remember we had like a nucleus. um, we've covered it recently. You have this nucleus, and then you have this orbit, or perhaps I shall say energy level number one. Then there is number two, number three, number four, right? And when we were talking about the ionization energy, we were talking about the outer shell. Now, I'm not talking about the outer shell, not about those valence electrons. I am talking about the electrons that are the closest to the nucleus. And so you guys can imagine that this is why you generate very large, it requires large energy to actually knock those electrons out. But what happens is that if and I'll show you in a second. So now I added two more energy levels and two and then three. And again, these energy levels, they're very unique for every single material. But what happens is that if I have an electron right here, okay, and now all of a sudden it's getting knocked out by the electrons that bombard my material, right? So I have this beam of electrons, right, that is accelerated toward my material. Now this little guy gets kicked out. Okay, so that means it's gone. So now there's an available space. So what's going to happen is that if you have an electron right here, it can jump down, okay, to take this spot that is now available. And because it's a lower energy. And if that jump occurs, we're going to see the signal, right? It's a very specific energy, which we already see. And specifically, this is actually going to be your K alpha, right? So that is going to be the jump from energy level 2 to energy level 1, okay? Now, K beta, it's the jump from level 3. So you can have an electron from here jump into here, and you will see another peak just like that. And once again, these peaks, and the rest is kind of like continuous radiation, right? But this specific peaks, right, it is exactly the transition that I'm demonstrating for you. Once again, the main concept here is that the reason the high energy X-ray waves are generated is because we are knocking out the inner electron, right? It's the electron that is right by the nucleus in the energy level 1, right? And so once that electron is gone, there's an available spot. And that means that the electrons from the higher energy, they can actually jump down and they can occupy those spots. But whenever you have a transition from a higher energy to the lower energy, there's always energy emitted. And that's why we see those X-rays, right? And once we detect them, we see these specific peaks, and these peaks are very, very unique. And this is how, by looking at the position, you can say, well, I'm looking, let's say, at pure molybdenum, or you can be looking at an alloy that has molybdenum and something else in there. Okay. Um, I'll actually give you a good example. I do not wish to stay like within the materials realm, within just the engineering. I'm going to give you an example of something that is relevant to the crime, okay, an investigation. X-ray technique is commonly used in crime discovery as well. And I will give you an example. Let's say at the crime scene, you found some dirt, right? And the dirt in everyone's backyard is very unique. Like there is a very specific composition. Some dirt has more iron, some is iron deficient, some dirt, I don't know. Let's say if you have a metal workshop, maybe your backyard has a bunch of nickel or lead or zinc, depending what you work with, right? So one of the ways to actually link a person to the crime scene through this dirt is by running an X-ray on the dirt. And what you do is that you're not actually interested in the dirt. You want to identify the metals, right? The tiny, tiny metals that are there, you'll be able to pick up by using the X-ray. Right, and there's actually one of episodes, I do not recall which specific series it was, but they used that specific technique to prove that the composition on the crime scene was identical to the composition of the dirt they discovered in a person's house on their boots. Okay, and it's kind of like almost like a fingerprint. Oh, perhaps you should think about the spectrum that you're looking at. This is a fingerprint, and every single material, right, metal, will have this unique fingerprint. All right. Now that these X-rays are emitted, right, off the surface, uh, there are a few things that can happen to them, and there are a few things that we can learn by using those X-rays. So something to keep in mind is that the crystal planes of the target metal act as mirrors, meaning that it basically once they basically reflect the X-ray beam, right? Now, the rays, okay, leaving a set of planes, they can either be out of phase, and that means that there's going to be no reinforced beam produced, or they can leave in phase, and that means that reinforced beams are produced, right? And this is exactly what we see on the picture here, right? You can either see no reflected rays, right? That means that they are out of phase, or you can have like a reinforced beam, right, of reflected rays, and that's because when they are the incident rays are in phase, okay? But for the X-rays reflected from different planes to be in phase, the extra distance traveled by a ray should be an integral number of the wavelengths alpha. Okay, and just so you understand, let's say if I have a ray one, okay, and it hits my plane one right here, okay, and then it gets reflected. For the second ray to be in sync, if you guys notice it, when the ray number one is already getting reflected, you will notice that this ray is going to be a little bit delayed, right? Like for them to be in sync, in other words, the second ray should travel this distance, which is going to be MP plus PN, and for the reflection to be in phase, that distance should equal an integer number of wavelengths, right? Because if you chop it as one half or anything but integer, they will be asynchronous, right? Now, if we ought to apply a little bit of geometry, we can also find out that either MP or PN, these are equal distances, right? They are also equal to the interplanar distance, which is your distance right here, okay? Or it's the same distance right here, multiplied by the sinus of angle theta, okay? So that means that I can now basically use this two. I can use one equation and equation two, and I can combine it into this one, right? Where you have an integer number of wavelengths is equal to 2 times the interplanar distance times the sinus of angle theta, right? Or we can write it just like this, right? For simplicity, we're just going to assume that our n is equal to 1, right? And this is also known as Bragg's law, okay? And this is going to be very, very helpful. If you guys will notice that usually um, when when we run this experiment, this is something that you already know, right? Because this is basically the wavelength that you are using during your experiment, right? And then these two is something that can be measured, and specifically the sine of theta. And this is exactly what it happens. And I will show you how exactly we're measuring that angle theta. We usually measure the double of that angle, right? We load powdered specimen, and for X-ray diffraction, we specifically use powders because it allows us to have this random orientation, okay? And so that means that we basically have different angles of incidence hitting the planes, right? Now, so once you have a radiation generator, you have this incident beam, and then once the reflection happens, right, then you can actually measure. So this is going to be your diffracted beam, right? And you can measure this angle, which is usually 2 theta, right? So to find the theta, you will have to divide it by 2, right? And you can also measure the intensity of this diffracted beam, the guy right here, okay? So let's look at the example, like what kind of information we can pick up from X-ray diffraction and how we can use it to identify parameters of our material, right? Sometimes to even find the material itself. Okay, so looking at the problem, we have a sample of BCC iron, right? This is your BCC iron, and it is placed in an X-ray diffractometer using incoming X-rays with a wavelength of, so we're using X-rays of 0.1541 nanometers, okay? This is given. Now, diffraction from the planes 110, right? So that means our H, K, and L is equal to 1, 1, and 0, was obtained at, so we see the diffracted beam, right? From the planes 110, and it was obtained at the angle 2 theta, which is 44.70 degrees, meaning that your theta is going to be, I'm just going to do conversion right away because you will need it later in the formula, 35 degrees. Now, question is, calculate the value for the lattice constant A, right? So we need to find the A. It, well, it is already a known value, right? But you will see how the value we will find in a little bit is going to be almost identical to the value that is recorded in the appendix of your textbook, right? We're going to use the following formula, knowing that interplanar space, right? I keep calling it distancing, space. What does that? Spacing, interplanar spacing. Is equal to A divided by the square root, and I will remind you the equation, H squared plus K squared plus L squared, which are the Miller indices, and they are given to us, right? It's 110. So if I am to plug in the numbers, I will end up with A divided by the square root of 1 squared plus 1 squared plus 0 squared. That would give me 2 squared, right? Now, so for me to find A, I need to know the interplanar spacing, right? So how do I do that? Well, I can find it from the Bragg's law. The Bragg's law states that the wavelength is equal to 2 times interplanar spacing times sinus theta, right? So from here, perhaps I can just plug it. Well, if I know that this is my D, I'm going to plug it in instead of here, and I will just express A right away, right? Which is going to be what? Lambda times square root of 2 divided by 2 sinus theta, right? Because I will express it for you, because you will end up with 2a sine theta divided by the square root of 2. So your A is going to be wavelength times square root of 2 divided by 2 sine theta. Now, if we ought to do the math, I got 0.2865 nanometers. And out of curiosity, I'm going to right away go into the textbook, or you may use the appendix files that are posted in supplementary uh, folder. Um, I always have to keep in mind that students use different editions and books. They don't really change much. So instead of telling you which page it is or which appendix it is, um, I'm just going to give you the name of the table that I'm planning to use. So I'm looking at well, in my book, in my edition, it's going to be appendix number 2 that says some properties of selected elements. Now I'm going to find iron. And if you look at it, BCC here, right, from appendix, it's going to be the lattice constant A for BCC is 0.28664 nanometers, right? So we are pretty close to that value. All right, so hopefully it makes sense, but this example shows you how you can obtain the information, right? And specifically, we basically got we knew the wavelength that we were using, but we obtained the theta, right? Usually it's the 2 theta angle. And that alone, and also we needed to know the plane from which we're getting the diffraction, right? From that alone, we are able to determine the constant, the lattice constant. And keep in mind that the lattice constant is unique. Let's say under certain circumstances, you may not know what the material is. And to find out what the material is, right? Sometimes you may be given a sample that you don't know what the sample is. Now you would go backwards, right? You would need to find the A and then go into the published data into the table. We will actually solve a problem like that too, where we'll try to find out which material we actually have loaded in the diffractometer, right? Now, to do that, we need to understand how we can interpret diffraction data. Now, instead of just giving you the final answer, which is going to be very, very easy, I will show you very quick the concept that is behind it, right? So, since we know that interplanar distance is your A divided by the square root of the sum of the squared Miller indices, right? And we also know this from the Bragg's law, right? So we know these two. So what's going to happen is that I'm going to take this D and I'm going to plug it in here, right? And this is how I end up with this equation. So I have a wavelength where I have the something in the numerator and the denominator. Now, from here, out of interest, do not ask me why. We do need to skip some of the points. But if I am to find the sine theta squared, right, I will actually end up with this equation. And there's something very, very unique. You will notice that if I am looking at the incoming and outgoing radiation, right, my wavelength is the same because I have the ability to actually define the wavelength of the beam I'm using. And then in addition to that, once the X-ray is deflected, right, or I should say diffracted, it is the same wavelength, so it won't change. And since I'm using same material, then my A remains the same. So if I am looking at different planes, so now I want you to think of this h squared, k squared, and l squared. If I'm thinking of different planes, right, you can have plane 1, 0, 0, and let's say 1, 1, 0, right? So, or we can just kind of like use, we don't have to define those planes. We can just say we have a plane A and a plane B, right? So for plane A, this equation is going to be this, right? for plane, this is your plane A, plane B, but you will instantly realize that this and this is going to be a constant for either. So if I am to take the ratio, I only need to know the Miller indices, right? Now, it turns out, right, certain planes diffract, right, meaning that you see a reflected beam under very specific conditions. For example, and that's how you can understand whether you're looking at a BCC material or the FCC material, right? Uh, for the BCC structure, the diffraction occurs only on planes whose Miller indices, when added together to a total, give you an even number. So once again, in the BCC structure, the planes that actually diffract the light, right, or perhaps reflect the light, only when your sum of H, K, and L is even. So if the sum is even, and let me guys give you an example. 1, 1, 0, right? Because 1 plus 1 will give me 2. It is even. That means the reflections are present. But if I have 1, 1, 1, then in the BCC, you won't see any diffraction. If it's a BCC material, then when we're trying to, the reflections from the plane 1, 1, 1 is going to be absent. Because per this rule, right? Now, what happens for the FCC structure? Diffraction occurs only on planes whose Miller indices are either all even or all odd. So this is not a sum anymore, meaning that your H, K, and L all even or H, K, L all odd. Example, 1, 1, 1. 0, 0, 0, and keep in mind your 0 is considered to be even, right? So you will be provided this table that summarizes everything for you, right? So what it means is, once again, so for FCC, all even or odd, and those would be 1, 1, 1, 2, 0, 0, and so on and so forth, but we're interested in the first two, right? In the set of the first two. Now, for the BCC, the rule is that the sum must be even, right? And that's going to be 1, 1, 0, the sum is 2, 2, 0, 0, the sum is 2, and then for the rest is going to be the same rule. And it turns out, if we ought to apply this rule, right, for the BCC crystal, the first two sets of diffracting are planes 1, 1, 0 and 2, 0, 0, right? It's right here. 1, 1, 0 and 2, 0, 0, and keep in mind the sum is even. And if you ought to plug in and do the math, you will see that the ratio is supposed to be 0.5. So if you are, and keep in mind guys, these values, right, these angles, this is something that you can easily measure. And hopefully you recall that from this sketch, right? You have the incident beam. Once it diffracts, you can actually see the angle, right? Meaning that I can identify both of these angles, right? For plane A, for plane B. Now, if the number is 0.5, that means I'm looking at the BCC crystal. For FCC, if I am to do the same, if I am to take the first two, right, the first two diffracting planes, which is going to be 1, 1, 1 and 2, 0, 0, and the rule is either all even or all odd. And if I am to plug in the numbers, then this ratio is going to be 0.75, right? So let's say if I have an unknown metal, right? Somebody brings me a metal and they do not know what it is, but they are very interested in finding out the origin of it. I'm going to load it and I'm going to perform a crystallographic analysis, right? Meaning that I can easily measure these values, right? And once I find the ratio, if my ratio is 0.75, right? That means I'm looking at the FCC crystal structure. If my ratio is 0.5, I'm looking at the BCC. Then from that moment on, this alone is not enough for me to tell which crystal it is, right? Because earlier we've seen that, well, we have a bunch of crystals that can be FCC, we have a bunch of crystals of BCC. So part of the crystallographic analysis is also find A, right? You need to find the lattice constant. And we just did an example like this, and I'll go back to show you. Just like this, right? And usually the wavelength is something that you know, and the angle is something that you measure. That alone allows you to actually identify. And not once, the only thing here is that our H, K, and L were given, right? Because they told us, well, because you're looking at the diffraction from 110, right? If you don't know, right? If you don't know, you would need to go to this step first, right? You would need to go to this step first to identify, well, am I at BCC or am I at FCC? And then you will find out the first reflecting, the first angle is going to be corresponding to the first plane, right? That actually reflects the light. Now let's look at the problem. So, and things will kind of like, I think everything will make sense, right? So let's say we have an X-ray diffractometer chart for an element that has either the BCC or FCC crystal structure and shows diffraction peaks at the following angles. These are two theta angles because keep in mind that's what you measure. I'm just gonna jump right away, right? Because my question is, well, I know that for my problem, I would need the first two angles and I need to divide them by two so I can actually find the angle itself. So I'm looking at the 20 degrees and at, wait, hold on, 25 plus 4, right? 29, okay? So I'm looking at these two angles, okay? So now wavelength, the wavelength of the incoming X-ray wavelength used was 1.154 nanometers. Okay, great. Okay, so basically I have theta A, right? For my plane A, the diffraction angle was 20 or reflection angle. The angle for the plane B is 29. And I know that the wavelength that has been used, because this is something that you can actually set up, right, manually, it was 0.154 nanometers. Okay. Step number one, I mean, to be honest, guys, yes, I'm breaking it down into three steps, so I'm guiding you how to do it. But typically in the exam, I'm not going to ask you for one, two, and three. I'm just going to say identify the element, right? But in here, to identify the element, I'm guiding you through steps that you should take to be able to do that. First is you need to determine the crystal structure. You need to know, well, is it BCC or is it FCC? And hopefully people remember is that I need to find this ratio, right? Okay, now that the angles are known, and if I am to plug in the numbers, right, keep in mind that you're using not the double angle, but a single, right, you will end up with the value that is roughly zero point 0.5. Now, because the ratio is 0.5, from here I can actually identify, okay, so I am looking at BCC, okay? I'm looking at BCC. This is identified. All right, we're one step closer. Next, we need to determine the lattice constant, right? You need to know the A, right? Without those two combined, you won't be able to identify the element itself. Now, since I'm going to work a little bit faster, uh, because my understanding is that people perhaps already people were exposed to problems like that, right? So I'm just reusing the formula that I've used in the previous lecture, in previous slides, right? So now keep in mind, one thing that I do need to know is I'm going to put the numbers in first, right? If I am to go, let's say BCC, and for simplicity, I'm going to go with the first diffracting plane, right? For the BCC, I'm going to go with 110. That means I will be also using the first diffracting angle, right? So that means here is I'm going to be 1 squared plus 1 squared plus 0 squared divided by 2 times sinus, and I'm using first angle, right? 20 degrees. Now, if I am to plug in the numbers, I believe the answer is going to be roughly 0.318 nanometers. Now, taking these two into consideration, that I'm looking at a material that has a BCC crystal structure, and the A should be a roughly 0.318. Now, keep in mind, this is the measurement, right? So there is a potential we won't be able to find this exact number, right? Because it's measurement, every experimental measurement carries an error with it, right? So meaning we can't assume that this is going to be the exact number. However, the material has to be BCC and the A has to be extremely close. So what I'm going to do now is that I'm looking at the appendix 2, which says some properties of selected elements, right? And I'm looking at the BCC, so I'm going to be looking at the lattice constant. I know that some students they like to take the third step. Since you know A and you know that this is BCC, you can actually use your prior knowledge, knowing how A is connected to the radius, and you can actually find the radius and then look just at the radius. But I'm gonna go with A, right? And I'm going down the table and I'm trying to identify. Okay, so far I am looking at 318. Okay, so the closest number is going to be tungsten, right? Why? And perhaps I'm going to do it in blue. It's going to be tungsten, right? Well, because it is BCC and the A is 0.31648 nanometers. I do not see anything closer than that. However, I almost skipped it. I almost skipped it with my eyes. Hopefully, somebody did look at it. If you look at the molybdenum, right, it is 315, right? So if you, that's going to be my one advice. Whenever you work with problems like that, do make sure in the exam you will have one problem where you have to identify the element. And I always give something that is a little bit tricky because there's going to be a few elements that are close, but you need to choose the closest, right? And I just realized that I somehow skipped it. The molybdenum is 0.315, right? And this one is almost 0.317, and this is why I'm going with tungsten. And the answer is actually tungsten. Now, for those who would like to practice a little bit more or kind of familiarize yourself with, I could give you something like that. I believe I took it from a different textbook, right? This is actually a tungsten, right? It tells you that this is a tungsten, which does have a BCC crystal structure. And in here is that you need to identify what do you need? Based on the information above, you need to find the radius, right? And it's very simple, guys. You already know the crystal structure. The sad part is that, of course, I will not give you an example like that because it already says BCC crystal structure, right? So I will not give you something like that. I will most likely erase that part, right? Because to find the radius, we need to find crystal structure, right? Crystal structure, either BCC or FCC. Well, here it's already given. I will tell you how I would offer a question like this in a second. Number two, once you know that, you can easily find A, and then once you know A, you can find the radius. This is a sad question, right? The reason it is a sad question because if you are a very good student, you might as well just go into the appendix, right, and pull up that number, right? Okay. Um, because the radius is also given in the table, right? So this is why I won't give you something like that because for examination purposes, I always provide you access to every single appendix that you can think of, right? Because I want to challenge you a little bit, but still have you in the comfort zone, right? But the beauty of this question, I would probably not disclose the material itself. I will not disclose that this is tungsten, and I will not disclose the crystal structure. So these two guys that are highlighted here would probably be not disclosed to you, but I will give you the peak diagram, right? And I will probably give you this exact angles that were used there, right? And keep in mind, these are 2 theta. So let's say, or let's say, even if the angles are not given to you, right? The best way is not to give you the angles. So how would you identify, is it BCC or FCC? The question will tell you that it's either BCC or FCC. Well, because you will look at this and you will say, okay, 110. For FCC, all has to be either odd or even. A 110, you already have odd and even, but the sum of it will give you 2. The sum of 2, the sum of 4, 4, and the sum of 4. And that's how you'll say, okay, well, I actually have here HK plus L equal to even, and that means I actually have BCC, right? So that would be a bit more interesting. Um, and the next question, I did say that I wouldn't give you the angles. Uh, well, it's better to give you something. However, you could clearly see that the angle here, the double angle here is 40. So the single angle is going to be 20, which is exactly what it is in here. So yeah, but hopefully you guys, this is typically, students love these types of questions because it's kind of like a puzzle. It's a riddle. And before you even know, before you even submit your work to me, you are able to find out whether you're right or not, because once you go to the appendix, right, and all the things need to align, right? The crystal structure, the A, and the radius. And if you've solved everything properly, there will be a correct answer for you there.